So, welcome all to the next problem solving session for the course Fundamentals of Food Process Engineering. So, in this week, we'll be solving problems related to week 10 syllabus, which includes the concepts of agitation and mixing. Moving to question 1, dash is a random distribution throughout a system of two or more initially separate ingredients. You have A, agitation, B, mixing, C, homogenization, and D, comminution. So we'll go through each of the topics one by one. So agitation establishes a particular flow within the pattern, and it's usually a circular motion within the container. And in case of agitation, you will mainly be dealing with a system that has only a single component. Let's say you have a container with water, and when you establish a flow pattern within the liquid, that is known as agitation. So when you have more than one component in your system and you want to mix those systems, that term that you use for a system with more than two components is called mixing. So mixing is a random distribution throughout a system of two or more initially separate ingredients. So mixing is where you have more than one component, and those two components can be either liquid-liquid, solid-liquid, or liquid gas as well. So in case of liquid-liquid, you might have two immiscible liquids and you're trying to make an emulsion, and you'll also have solid liquid and gas liquid in the mixing process. And a comminution is the size reduction processes that we discussed in the previous week's videos. So a single homogeneous material can be agitated but cannot be mixed until some other material is added. So as I said, agitation is the term you prefer for a system having a single component, and when you have more than one component, you use the term mixing, where two initially separate ingredients are mixed to get a homogeneous material. So answer is option B. Okay, moving to question 2. The ribbon blenders are used for A, liquid, B, dough and paste, C, powder, and D, all of the above. So different kinds of, one of the frequent questions that you'll be encountering in the assignments as well as your other questions is that you'll have to relate a certain kind of blender to its application. So that will be the kind of mainly questions that are being time and again asked. So we'll deal with a few questions here in this problem solving session. So one of the mixer agitator is the ribbon blender, where you will have something like this. So you have a trough or a container where you can feed in your material, and you have a ribbon shaped blender as you can see here. So in a ribbon shaped blender, you will have an inner helical blade and an outer helical blade. So the inner helical blade and the outer helical blades will move in opposite directions and at different speeds to enable mixing process. So each kind of blender will be used for a particular kind of food material. You cannot use any blender for any material. So each of the blenders will be used for a particular kind of material. So ribbon blenders are specifically used for powders, fine solids. So ribbon blenders are powder mixers used to mix solid powder particles. The equipment has a trough or a container with ribbon shaped blades as you can see here, and these ribbon shaped blades are mounted onto a horizontal shaft, the black color shaft that you see here. And these ribbon blenders will have an inner helical blade and an outer helical blade rotating in opposite directions and at different speeds to enable the mixing of the powder. So ribbon blenders are specifically used for powders. The answer is option C. Moving to question 3. We have statement 1. The diffusion mixing refers to the movement of group of particles because of the direct action of the impeller or a moving device. And statement 2. The shear mixing refers to the random dispersion of individual particles in the interparticle void spaces throughout the mixture. So in this particular question, you are dealing with two kinds of mixing that is being discussed here. So in the video lectures, if you go through, the faculty would have discussed three kinds of mixing, and we'll look at all of those one by one. So first kind of mixing is the convection mixing. It is also known as macro mixing, where you have a movement of group of particles. As you can see here, a group of particles will be transferred from one position in the container to another position. That is, the group of particles will be mixed because of the direct action of the impeller or a moving device. So one of the impeller that is used is the trough mixer with a spiral ribbon. So this is used to establish a convection mixing. And as I mentioned, convection mixing is also known as macro mixing, and the rates of this mixing are very fast because you have the direct action of the impeller. The rates are pretty fast, but at the micro level there will not be any mixing. So as you can see here inside the box, within this box you do not see much of a mixing. You do not have equal homogeneous mixture of the yellow and the blue particles here. So at the micro level you will not establish a homogeneous mixture, but at the macro level you can see the mixing happening at very high speeds. So when you have a mixing process, a pure convection based mixing is not preferred, because although at macro level you will be mixing the substance, at the micro level it will still not be homogeneous. So the other kind of mixing is the diffusion mixing, where you will have the particles, you will have a random distribution or random dispersion of the individual particles at the interparticle white spaces throughout the mixer. So you will have mixing at the micro level here, with the individual particles being mixed. So diffusion is also known as micro mixing. And diffusion, since it's at the micro level, the rates are very slow. The rate of mixing is extremely slow. So as you can see here, you can have a diffusion based mixing throughout, but since the rates are very slow, it is not preferred. So generally when you mix a certain substance, we have a combination of these mixing mixing techniques. That is the convection mixing, the mechanisms, the convection mixing, diffusion mixing and shear mixing. All these mechanisms are involved to establish a homogeneous mixture both at the macro level as well as the micro level. So convection is known as macro mixing, that happens at a very fast rate, but is still not homogeneous at the micro level. Whereas in case of diffusion, the mixing will happen at the micro level with individual particles, but then the rates will be very slow. The third type is the shear mixing, where a group of particles are mixed through the formation of slipping planes. So you have different planes here that contain particles, and these planes are formed because you have a velocity distribution inside the container. So with the action of an impeller, you can see that the velocity would be very high close to the impeller, but close to the walls of the container your velocity will be very low. So at different points of the container you have different velocities of the particle, and hence you get a velocity distribution. And because of this velocity distribution and momentum transfer, you have the development or formation of a slipping plane, which will then be mixed. The particles across the slipping planes will be mixed, hence causing a shearing action or a shear mixing mechanism. You will have mixing of the or the shearing of these slipping planes that will hence cause the mixing, and the rate of these shear mixing is somewhere intermediate between the convection and the diffusion. So convection is very fast, diffusion is very slow, and shear mixing is somewhere in between. So after shear mixing, you will also have, in order to have a proper homogeneous mixture, you will also need to have convection as well as diffusion mechanism. So as you can see here, all the three mechanisms involve a slightly different way of mixing, but then establishing all these three inside your container will ensure that you have a homogeneous mixture at the end. So when it comes to statement 1, when you have a movement of group of particles, you are referring to convection mixing and not diffusion mixing. So statement 1 is false. And in statement 2, you are looking at individual particles being mixed in the interparticle void spaces. So that becomes diffusion mixing, and hence statement 2 is also false. So the answer to this question is option D. So question 4, again you have where you have to relate a certain kind of mixer to its application. So these are pretty recurring questions. So which of the following mixer is more suitable for mixing dry powders. So you have 4 different kind of mixers given: A kneader, B pony mixer, C turbine mixer, and D vertical screw mixer. We'll go one by one. So kneaders and pony mixers are used for cohesive solids or solids that stick to each other. One of the examples of such cohesive solids are dough and paste. So for cohesive solids, you use these mixers, which are kneaders and pony mixers. Some of the other examples are change can mixer, dispersers and masticators, mixer extruders, and mixing rolls. So you have all these examples, all these discussed in the video lectures if you want to go through more details. So kneader and pony mixers are used for cohesive solids, and turbine mixer is used for liquids, especially low viscosities, or liquids that are not of high viscosities rather. So turbine mixers are used for liquids, and for non-cohesive solids such as powders, you use tumbling mixers, ribbon blenders, as we discussed in the previous second question, and then you have a vertical screw mixer and then fluidized bed mixer. So in a vertical screw mixer, the shaft will be vertical and you'll have a screw shaped mixer surrounding the shaft or mounted onto the shaft. So those screw will help in mixing of the dry powders or non-cohesive solids. So vertical screw mixer is the mixer that is more suitable for dry powders. And for mixing liquids, you have paddle, propeller, as well as turbine. So answer here is option D. A and B are for cohesive solids, C is for liquids, and D is for dry powders. Okay, question 5. So questions regarding the velocity component are also very frequently asked in the assignments. So which of the following velocity component acts in a vertical direction in a liquid mixer? So you have A radial, B axial, C tangential, and D combination of radial and tangential. So you have 3, as mentioned in the question here, you have 3 different kinds of velocity components that are being discussed. So just to give a pictorial representation of these 3 velocity components, you have radial here, where the velocity component acts in a direction perpendicular to that of the shaft. And then you have axial, where the velocity component acts parallel to the direction of the shaft, giving an axial flow. And then you have tangential flow, where the velocity component acts tangential to the circular motion or the impeller blades inside the container. So we'll be discussing in a little more detail as we discuss the questions for these velocity components. So which of the velocity components acts in a vertical direction in a mixer, which means in this direction. So this direction is parallel to that of the impeller shaft. So that corresponds to the axial flow. So in an axial flow, the liquid moves in a direction parallel to the shaft, reaches the bottom of the tank and then rises upwards before encountering the suction by the impeller. And often propellers are used for axial flow pattern of liquids and to ensure mixing of suspensions. So different kind of agitators or mixers are used for for establishing different velocity components. So in this case, for axial flow, we use propellers to ensure that the velocity component acts majorly in the vertical direction or parallel to the shaft. So answer here is option B. Question 6. Power number is the ratio of A. Inertial force to viscous force, B. Inertial force to gravitational force, C. External force to inertial force, and D. Reynolds number to Froude's number. So the power consumption. So if you are trying to mix 2 components inside your system, you have to give certain power to the impeller or to the mixer to mix the system, to mix the components. So a power consumption in a mixed system can be related to its operating variables by something known as a power number. So power number is a dimensionless number that relates the power consumption to the operating variables. And when I mean operating variables, those include the properties of the fluid such as viscosity, density, and the other operating variables such as the impeller speed, the impeller diameter, and so on. So it relates the power consumption to the operating variables with the help of a dimensionless number known as the power number, and this power number is the ratio of external force to inertial force, and this power number is a function of Reynolds number and Froude's number. So it is not the ratio of Reynolds number to the Froude's number, it is a function of this Reynolds number and Froude's number, and a power number can be denoted as NP here, which is equal to P divided by rho Ni cube di power 5, where P is the power consumption in the system, rho is the density of the fluid, Ni is the speed of the impeller in revolutions per second, and di is the diameter of the impeller. So as you can see here, it relates the power consumption with the operating variables in the mixing system, and the NP is the dimensionless number, and NP is a function of Reynolds number and Froude's number, where Reynolds number is the inertial force to viscous force. So the ratio of inertial force to viscous force is actually Reynolds number. The inertial force to gravitational force ratio is Froude's number, and external force to inertial force is the power number. So we will be discussing more on the power number, and the problems related to power numbers are actually very important and have been very recurring questions in the assignments. So for this question, the answer is option C. So question 7. Which of the following mixer is more suitable for mixing of viscous fluids? So you have A. kneader, B. turbine agitator, C. anchor agitator, and D. tumbling mixer. So if you remember our previous question that we discussed regarding the mixers, kneaders are used for cohesive solids such as dough, paste, and so on. And turbine agitators are used for liquids, but then we do not prefer highly viscous fluids. And then you have anchor agitators, which is used for viscous fluids, and I'll be showing you the example of an anchor agitator as well. And then you have tumbling mixers, which are used for non-cohesive solids. So an anchor agitator looks like this, where your agitator looks like in the shape of an anchor, and these anchor agitators are low shear agitators. So for high viscosity blending, we use a low shear impeller that keeps the fluids at a uniform viscosity in the blending tank. So the entire purpose of mixing two components is that you need to make sure that throughout the container, at any point in the container, the properties of the mixture remains same, or the properties of the mixture remains homogeneous throughout the container. So if you use a low shear impeller, it helps to keep the fluids at a uniform viscosity throughout the blending tank. And it often makes sense to use a close clearance impeller such as a spiral or an anchor style impeller to keep the uniform viscosity in the blending tank. But if you use a high shear impeller, what will happen is that you will have different viscosities at different points. You will have a different viscosity at the regions very close to the blender or the impeller blades, and at regions very far from the impeller blades, you will have a different viscosity, which is something that you don't want. You need to ensure that all the properties remain same throughout the container. So for this, we use a low shear impeller that ensures that all the contents of the container are mixed adequately. And an example of this low shear impeller is the anchor agitator or a gate agitator. So the answer to this question is option C. Question 8. Which of the following velocity component tries to move a liquid in a circular motion on a horizontal plane? So again, we are dealing with questions related to velocity component. Again, your A is for radial component, where your velocity component is perpendicular to the shaft. Then you have your axial velocity, which is parallel to the shaft. And then you have your tangential velocity, where the velocity is tangential to the circular motion. So in a tangential flow, the liquid moves in a circular motion in a horizontal plane, and the velocity component is tangential to the circular flow of the liquid and at very high speeds. So you need to maintain a certain speed to ensure proper mixing when you're establishing a tangential velocity inside the system. But if you go for very high speeds, you will have something known as a vortex formation, where as you can see here, you will have your components being thrown out towards the walls of the container due to the centrifugal force. So when you spin it at a very high speed, you will the particles will experience a centrifugal force, and everything will start accumulating towards the walls of the container. And that is something you don't want, because you need to make sure that this all the solid particles are being mixed completely instead of being accumulated at one end. So apart from this non-homogeneous mixing, you will see that a large portion of your shaft is exposed to air instead of being exposed to the liquid, which means that the majority of the power that you're supplying to rotate this impeller is going waste, because it is not even in contact with the liquid, it is in contact with air. So both for power requirements and for the fact that you're not exactly mixing the components properly, a vortex formation is not preferred in a system. And hence, to prevent these vortex formation, we use something known as baffles, as seen here. These vertical things that you see in the diagram are called as baffles that disrupt this vortex formation and hence ensures proper mixing. The answer here is option C. We'll be discussing more on vortex formation in the upcoming slides as well. Okay, this is again a repetition. Question 9. Statement 1. Axial velocity component acts in the direction perpendicular to the impeller shaft. And statement 2. The radial flow follows a circular path around the shaft and creates a vortex in the liquid. So, going to first statement 1. The axial velocity does not act in the direction perpendicular. It is the radial velocity that acts in the direction perpendicular. And the velocity that follows a circular path around the shaft is the tangential velocity. So the tangential component acts in the direction tangent to the circle of rotation and creates a vortex, as we discussed in the previous slide. And it's the radial component that acts in the direction perpendicular to the impeller shaft, and axial component acts in the direction parallel to the impeller shaft. So for this it is the radial velocity, and for this it is the tangential velocity. So both the statements are false. The answer to this question is option D. So as you can see here, velocity component is a very crucial topic in this particular week's syllabus. Going to question 10. The power requirement in a liquid mixer is a function of Reynolds number and Froude's number. And statement 2. When the impeller Reynolds number is less than 300, the Froude's number is ineffective. So first, going to statement 1, as we discussed in one of the previous slides, the power number is a function of Reynolds number and Froude's number, and it can be given, if you are writing a power number equation, it can be given as NP is equal to a function of Reynolds number power n and Froude's number power m, where n and m are certain constants, and the value of n and m will depend upon what kind of a system you are looking at. It will depend upon the kind of fluid, whether it's Newtonian or non-Newtonian. It will depend upon the system, whether what kind of an impeller you are dealing with, how many blades it has, and so on. So depending on the system conditions, where n and m, that is this NP relation with its Reynolds number and Froude's number, will vary. And we'll be looking at certain problems towards the end of this problem solving session. So yeah, Reynolds number is the ratio of inertial force to the viscous force, and Froude's number is the ratio of inertial force to the gravitational force. And power number is a function of these both numbers. And impeller Reynolds number can be given as rho ni di square by mu, and Froude's number can be given as di ni square by g, where rho is the density of the fluid, ni is the impeller speed, di is the impeller diameter, mu is the viscosity, and g is the acceleration due to gravity. And whenever you calculate the impeller Reynolds number, if that is less than 300, then your Froude's number becomes ineffective. That is, the effect of your gravitational force is not that strong. Yeah. When you're dealing with impeller Reynolds number less than 300, the gravitational effect is not that significant. Hence, you need not include the Froude's number into calculation. So answer is option A. That is, both the statements are true. Moving to question 11. Which of the following statement is true? You have A, mixing index increases with time, B, mixing index decreases with time, and C, mixing index is constant for a particular fluid, and then D, mixing index reduces with half the time. So before we answer this question, we need to first know what is a mixing index. Mixing index of a real mixture can be given as follows, where m is equal to s naught square minus s square by s naught square minus s infinity square, where s naught square is the variance of a segregated system. So when you mean by variance, it is exactly the same definition as that you see in statistics. So s naught square, where s is given as root of summation I equal to 1 to n xi minus x bar the whole square by n. So S naught is the variance of a segregated system, that is at time t equal to 0. Yeah. And S is the variance of the real mixture at time t. And S infinity is the variance of a fully mixed system. Yeah. So when at time t equal to 0, the components of your system will not be mixed, they will be segregated. So the variance calculated at time t equal to 0 will be the variance of a segregated system, also known as S naught square. And S square is the variance of the real mixture at time t. And S infinity square is the variance of a fully mixed system, that is at time t equal to infinity, where S can be given as root of summation I equal to 1 to n xi minus x bar the whole square by n. So we will be solving a lot of problems related to this mixing index. So what generally happens is that when you have a container being mixed with different components inside it, at a particular time, let's say at time t equal to 5 minutes, you will take certain number of samples from the container, some small amount of samples from the container. So let's say you're taking 10 samples. In those 10 samples, you will be calculating the fraction of your desired component. Let's say component A, you have component A and B, and component A is what is your desired component. So the fraction of component A in that mixture in each of those 10 samples can be given as xi. And x bar will be the average fraction of your component A in all of those 10 samples. So that will be x bar. And small n will be the number of samples that you have taken at that particular time. So from there you can calculate what is S square, that is the variance at time t. In the upcoming problems, we will also see how to calculate S naught square and S infinity square. But for as of now, this is the formula that you need to remember. So as you can see here, at time t equal to 0, your S square will be close to S naught square, which means that at time t equal to 0, your mixing index will be close to 0. As time increases, your xi will start approaching x bar. That is, as you keep mixing it more and more properly, the weight fraction that you calculate in each of the samples will be very close to the mean fraction of the samples. Or another way to look at it is that as you increase the time, it will start approaching the fully mixed system, which means that S square will start approaching S infinity square. So if S square starts approaching S infinity square, M will start increasing all the way from 0 all the way to 1, which means that as time increases, your mixing index will also increase from almost nearly 0 to nearly 1. So now to look at it, as the time increases, the system gets more and more mixed, and hence the variance S reduces over time, or it starts to approach S infinity square. That is, the difference between the fractional component, that is xi, and the mean fractional component x bar reduces. If the difference reduces, then your S square will also automatically decrease, and if S square decreases, your M will increase with time. So another way of looking at it is that you can also understand how mixing index increases with time if you look at the formula for the rate of mixing. So the rate of mixing is directly proportional to the amount of mixing still left to be done at that particular time, which means that dm by dt is proportional to 1 minus m, because it is proportional to the mixing that is still left to be done. So it is 1 minus m. So dm by dt is proportional to 1 minus m, and if you remove the proportionality constant, you can if you remove the proportionality sign, you can multiply your RHS with the proportionality constant. So dm by dt is equal to k into 1 minus m. So when you integrate this this equation, you get ln, that is natural logarithm of 1 minus m, equal to minus kt. And please note that for a particular kind of a system, let's say for a certain component A and B, your k will remain constant irrespective of the time, which is why it is known as mixing constant. Your k will remain constant and only your m and t will keep varying. So if you now want to look at it, m is equal to 1 minus e power minus kt, and as time increases, e power minus kt reduces. Since as time increases and e power minus kt reduces, m will approach more and more 1, and that is m will start increasing. So this is also another way to look at mixing index increasing with time. So the answer here is option A. Okay, we will solve one of the problems related to mixing index, which is also a very crucial topic in the week's syllabus. So the mixing rate constant, that is the K, is given as 0.012 second inverse in a mixing process. So after 6 minutes of operation, what will the mixing index be? So as I said, the only equation that relates the mixing index with the time is the rate of mixing equation. And the rate of mixing is proportional to the amount of mixing still left to be done at that time. So the rate of mixing can be given as dm by dt is equal to k into 1 minus m. Integrating this, we get natural logarithm ln of 1 minus m equal to minus kt. So you have time, which is 6 minutes. You need to convert that into seconds. And you have k, which is in second inverse, which is 0.012. So it's just a mere substitution problem, where ln of 1 minus m is equal to minus 0.012 into 6 minutes, and then I'm converting that into seconds. So I'm multiplying it into 60. So minus 0.012 second inverse into 6 into 60, which is 360 seconds. So 1 minus m is found out to be 0.0133, and hence m is equal to 0.987, which is option D. So you will be encountering a lot of problems related to mixing index. So question 13. The vortex formation can be prevented by A. Positioning the mixer shaft off the center, B. The use of baffles, C. Installing two sets of impellers rotating in the opposite direction, and D. All of the above. So if you remember, a tangential flow component, tangential flow or a tangential velocity component acts in the direction tangent to the circular motion. And when you have very high speeds involved, you will have something known as a vortex formation, where half of your a major portion of your impeller will be in air, and all your particles, that is your solid suspension particles, will be thrown out towards the walls of the container due to the centrifugal force, because of which you will have accumulation of your solid particles in the corners and your system will not be mixed uniformly. And in addition to that, since your shaft is now rotating in air, you will have a lot of power wastage because your liquid is not being in contact with the shaft at all. So because of this, now we need to prevent vortex formation, and that can be done by multiple methods. A, you can position the mixer shaft off the center. That is, instead of keeping the shaft at the center, you can keep it at a certain at a distance away from the center, or you can keep it at a certain angle. Either of these will help in the prevention of vortex formation. Another technique that you can use is the use of baffles. If you have baffles in your system, then this vortex formation is prevented and you have a much more thorough mixing happening. Another technique to prevent the vortex formation is to install two sets of impellers, each of them rotating in an opposite direction. So if you have more than two sets of impellers rotating in an opposite direction, you will not have this kind of a circular motion being established, and hence you will prevent vortex formation. So all of these techniques, in a vortex, the particles experience a centrifugal force and are thrown towards the walls. The large solid particles settle down at the bottom, hence resulting in very poor mixing, and hence vortex is prevented by the use of baffles that disrupt the circular motion, or positioning the mixer shaft off the center, or placing the shaft at an angle. And vortex can also be prevented by the use of two sets of impellers rotating in an opposite direction. So all of these techniques can be used to prevent the vortex formation and hence to enable proper mixing. The answer to this question is option B. So question 14, which is again a mixing index problem. The mixing rate constant can be determined as 0.016 second inverse. Calculate the mixing time required to achieve a mixing index of 0.95. So the previous question, you had the time given and the mixing constant given, but now you have the mixing constant and the mixing index given, from which you have to calculate the time. So the rate of mixing here is proportional to, again the same equation we will be using, it is proportional to the amount of mixing left to be done. So dm by dt is equal to k into 1 minus m. Integrating, you get ln of 1 minus m equal to minus kt. So you substitute the m value and the k value and calculate the time. So ln of 1 minus 0.95 is equal to minus 0.016 second inverse into time. So since k is in second inverse, the time that you get will also be seconds, in seconds. So time comes out to be 187 seconds. So please ensure that your units are consistent. So it's the time that is 187 seconds, and hence if I convert that into minutes, I get 3.12 minutes. So please ensure that your the units you are noting down are correct, so that you do not get confused within the options. So the answer here is option B. Moving to question 15. In a mixing operation, 15 kgs of active compound and 85 kgs of inert material are mixed. The result in weight percent of active compound after mixing for 10 minutes were 21.8, 21.8, 23, 21.4, 22.3, 22, 22.7, 20.9, 22 and 21.7%. Calculate the mixing index after 10 minutes. So here you do not have the mixing constant and all. So you cannot use the rate of mixing formula here. Instead, we'll use the variance formula for the mixing index. First, what is happening here is that you have 15 kgs of active compound mixed with 85 kgs of inert material, and you're trying to track this active compound and see how well it is mixed. So the fraction of the active compound at time t equal to the fraction of the active compound is 15 divided by 15 plus 85. That is the amount of active compound divided by the total amount of substances present inside the container. So 15 divided by 15 plus 85, which is equal to 15 divided by 100. So the fraction of active compound is 0.15. So that is something that you need to calculate. And what is happening here is that after 10 minutes of mixing, you're taking 10 different samples and calculating what is the weight percent of this active compound in each of those samples. And that is what you have the data here. So we need to calculate what is the mixing index after 10 minutes. So mixing index of a real mixture can be given as m is equal to s naught square minus s square by s naught square minus s infinity square, where s naught square is the variance of a segregated system, that is at time t equal to 0. S square is the variance of the real mixture at time t. S infinity is the variance of a fully mixed system, that is at time t equal to infinity. And S square can be calculated as summation of I equal to 1 to n, where small n is the number of samples that you have taken. That is, here we have taken 10 different samples, so n will be equal to 10 here. Summation of I equal to 1 to n, xi minus x bar the whole square by n. So we need to calculate what is S naught square, we need to calculate what is S square and S infinity square. So we will first start to calculate what is S square here. So I am creating a table here where I have taken 10 different samples and I have noted down the weight fraction of each of those samples. So in the question, weight percent is given. I am converting that into weight fraction by dividing it by 100. So the weight fraction of each of the samples are noted in the first column, and I am averaging all of those to calculate what is x bar for the formula. So that I get as 0.2196. Then I calculate what is x minus x bar. That is 0.218 minus 0.2196, which gives me minus 0.0016. So similarly, I calculate for all the 10 samples x minus x bar. Then I am squaring this value, which is x minus x bar the whole square, and then I am adding all of this up. So this will be equal to summation of I equal to 1 to n x minus x bar the whole square. So I have calculated what is x, I have calculated x bar, and then calculated x minus x bar the whole square for each of the samples, and then added all of it. So that divided by small n, which is the total number of samples, will give you S square at time t equal to 10 minutes. So 0.003304, which is your x minus x bar, the summation of x minus x bar the whole square, divided by small n, which is the total number of samples. That gives me an S square value of 3.304 into 10 power minus 5. So we have calculated what is S square. We still do not know what is S naught square and S infinity square. So for S naught square for an unmixed, that is for an unmixed solution, S naught square is equal to P into 1 minus P, where P is the weight fraction at time t equal to 0. So at time t equal to 0, you had 15 kgs of active compound and 85 kgs of your inert material. So your P is equal to 15 divided by 100, that is 15 divided by 85 plus 15. So 15 divided by 100, which is 0.15. So the P value is the weight fraction at initially, which is 0.15. So from there you can calculate what is S naught square. So 0.15 into 1 minus 0.15 will give you S naught square, which is equal to 0.1275. So in order to calculate S infinity square, that is for a fully mixed system, S infinity square is equal to P into 1 minus P divided by capital N. Please note here that capital N and small n that we used in the previous slide are not the same. Capital N refers to the total number of particles present inside your mixing container, and small n is the number of samples that you have taken out. at a certain time. So in the question, it has not been mentioned how many particles are there inside the container. So you can assume it to be a very very large system with infinite number of particles. So if you have infinite number of particles, n will be equal to infinity, and hence S infinity square will go to 0. So if the number of particles in the system are given, then you can substitute the n value and calculate S infinity square. For all the problems where the particle number is not given, assume it to be infinite number of particles and keep S infinity square as 0. So now you have S square that you calculated from the table, S naught square from here, and S infinity square as 0. From there you can just directly plug in the values inside the equation and calculate the mixing index or M. So mixing index is equal to 0.1275, which is S naught square, and S square that we calculated in the previous slide, which is 3.304 into 10 power minus 5, divided by S naught square minus S infinity square, which is 0. So M comes out to be 0.9997, and hence the answer to this question is option B. So just giving a recap, when you have multiple data, when you have taken out multiple samples and you've calculated the mixing, you've calculated the weight percent in each of those samples, what you do is you create a table where you calculate the variance at that particular time. That is, first you calculate the mean, then you calculate x minus x bar the whole square for each of the samples. Then you add all these to get the summation of x minus x bar the whole square. That divided by small n, which is the total number of samples, will give you S square. S naught square can be given as P into 1 minus P, where P will be the weight fraction initially in the mixing operation. And S infinity square will be P into 1 minus P by N, and it will be 0 for a system where you have infinite number of particles. Then you plug in the values and calculate M. So you need to calculate M through the variance concept if you do not have the mixing constant given in the question and there is no other way of figuring it out. Okay, so moving to the next question. So these questions similar to question 15 have been discussed in the video lectures as well and has been a recurring problem in the assignments. Question 16. The initial proportion of the vegetable powder to starch in a mix is 40 to 60. The variance of the sample after 4 minutes is 0.09. So how much time does it is required to reach a variance of 0.05? So assume a large sample size, which means you have to assume that capital N is equal to infinity. So in this particular question, you do not have the sample details given. You do not have 10 samples and you do not have the weight fraction of each of the samples. Instead, they have directly given you what is the variance of that particular time point. That is after 4 minutes. So if for 4 minutes your variance is 0.09, what is the time required to calculate to reach a variance of 0.05? And you have the p value given here. P value can be calculated as 40 divided by 40 plus 60, and hence p value is 0.4. So with this, very similar to the previous question, we calculate what is S naught square, we calculate what is S infinity square. S square is already given here as 0.09 and time is given as 4 minutes. So with this, S naught square is equal to P into 1 minus P as we discussed in the previous slide. So S naught square is 0.4 into 1 minus 0.4, which is equal to 0.24. And S infinity square is 0 because you're dealing with a large sample and hence you're assuming capital N to be infinity. So P into 1 minus P by capital N is the formula for S infinity square. And since N is infinity, S infinity square goes to 0. So I'm plugging in the values here. S naught square was 0.24 as we calculated. S square is given in the question as 0.09 and S infinity square was 0. From this you can say that at time t equal to 4 minutes your mixing index or M was 0.625. So the only way you can relate mixing index to the time point, the time is by employing the rate of mixing equation, where dm by dt is equal to k into 1 minus m. This is something that we have been discussing previously also. So ln of 1 minus m is equal to minus kt. So now you substitute the m value here, and you already know that this m value was for 4 minutes as given in the question. So you know the t value as well. So from m and t, we get from this equation, if you know m and t, you can calculate k, which is the mixing constant. So ln of 1 minus 0.625 is equal to minus k into 4 into 60. So I am converting minutes into seconds. So I am multiplying it into 60. With this, you get a k value of 4.0868 into 10 power minus 3 second inverse. And for a particular kind of component, or for a particular kind of system where you are dealing with, say, component A and B, your k will remain constant throughout the mixing process. So now that you know that k remains constant for the mixing process, you have k, you have the variance at some other time, which is given as 0.05. From that you can calculate what is m. So now that you know m and k, you can calculate time. So what I mean is, to reach a variance of 0.05, you now substitute s square as 0.05 here instead of 0.09. Your s0 square and s infinity square will remain the same. So 0.24 minus 0.05 divided by 0.24 minus 0, which gives a mixing index of 0.792. So now that you know the mixing index at some other time point, and you already know what is the mixing constant, you can calculate what is the time for this particular mixing index. So ln of 1 minus m is equal to minus kt. I am substituting m value as 0.792 and k value that we calculated as 4.0868 into 10 power minus 3 second inverse into time. From this, you can get a time of 384 seconds. So please note here that, as we said, mixing index increases with time. So at 4 minutes or 240 seconds, your mixing index was 0.625. But at 384 seconds, your mixing index is 0.792. So as you can see, as you keep on increasing the time, your mixing index increases and approaches 1. So the answer to this question is option C. Okay, question 17. The agitator with a flat blade having a diameter of 0.45 meter operating at 125 rpm is used to mix the liquid sample of density 1028 kg per meter cube and viscosity of 0.03 pascal second. The power number obtained for the agitator is 5. So we need to calculate the power requirement for mixing. So if you remember, power number is the dimensionless number that relates the power requirement for mixing to its operating variables. So here given that is Np is equal to P divided by rho Ni cube di per 5, where P is the power consumption or the power requirement, rho is the density of the fluid which is given in the question, Ni is the impeller speed in revolutions per second, and the impeller speed is given in revolutions per minute in the question. We just need to convert it into seconds, and di is the diameter of the impeller, which is also given in the question. So it's a basic substitution formula, and Np, which is the power number, is also given in the question. So since all of the other variables are given, we need to calculate what is P here. So I'm substituting the values. 5 is equal to P divided by 1028 kg per meter cube. RPM, I'm converting it into RPS by dividing it by 60. So 125 divided by 60 the whole power cube, and diameter 0.45 bar 5. So it's a straightforward question, and from this you can calculate the power requirement to be 858 watts, and hence the answer is option A. So question 18, which is the last question for the problem solving session. A non-Newtonian fluid is agitated in a tank of diameter 0.8 meter with a 6-blade turbine of 0.4 meter diameter rotating at 180 rpm. Calculate the power requirement for the agitator using the empirical equation. NP is equal to 0.4486, Reynolds number 0.4587. Given the fluid properties, K is equal to 13, N is equal to 0.58, density is equal to 968 kg per meter cube, and average shear rate is 10 into N, where N is the number of revolutions per second of the agitator. So in the previous question, apart from the operating variables, we had the power number, so it was a direct question to calculate the power requirement. But in this problem, you do not have the power number. In fact, instead of that, you have the empirical equation for the power number. So in order to calculate the power number, you need to know what is the Reynolds number. And in order to know the Reynolds number, you need to know what is the viscosity and the fluid properties. So since we are dealing with a non-Newtonian fluid, you will calculate something known as the apparent viscosity, and that is something that we discussed in the very first week of this course. So we'll just look at the given here. Given dt, which is the diameter of the tank, is 0.8 meters. The diameter of the impeller is 0.4 meters. And I'm converting the speed of the impeller speed from RPM to RPS. So I'm dividing 180 by 60, and hence my N is 3 RPS. And you have the K value and N value, that is the consistency index and the flow behavior index, given as K equal to 13 and N is equal to 0.58. And rho is the 968 kg per meter cube, and average shear rate, that is gamma dot, is equal to 10 into N, where N is the number of revolutions per second of the agitator. So I'm first calculating what is the average shear rate, which is 10 into N. So 10 into 3 is equal to 30 second inverse. And if you remember, for the apparent viscosity of a non-Newtonian fluid can be given as mu apparent is equal to K into gamma dot per N minus 1. So from the problem, you have K given as 13, you have N as 0.58, and you just calculated gamma dot to be 30 second inverse. So with this, you can calculate the apparent viscosity of the fluid, which is 13 into 30 power 0.58 minus 1, which is equal to 3.116 Pascal second. So now that you have the viscosity of the fluid, you can calculate the Reynolds number, and from the Reynolds number, you can calculate the NP or the power number. Now that you have the power number, it is very similar to the previous question. You just calculate the power requirement. So first we'll go with calculating the Reynolds number, which is equal to rho Ni di square by mu. So we have all the variables required to calculate the Reynolds number. The density is given as 968 kg per meter cube. Ni, which is the speed of the impeller in RPS or revolutions per second, is given as 3. Di, which is the diameter of the impeller, is 0.4 square, and then mu, which we just calculated as 3.116 Pascal second. So by substituting all these values, you get a Reynolds number of 149.11. And this is the correlation that is given in the question for this particular turbine system and the fluid flow properties. So NP is equal to 0.4486 Reynolds number per 0.4587. So this is the correlation that will keep changing with the kind of with the kind of impeller that you are using, the number of blades, the kind of fluid that you are using, and so on. So this correlation is not constant, it will keep depending based on the system. So NP is equal to 0.4486 Reynolds number per 0.4587. So now that you have the Reynolds number, you just substitute it inside this equation. So NP is equal to 0.4486 into 149.11 per 0.4587. From there, you can calculate the NP as 4.454. So now that you have the NP or the power number, you have the density, you have impeller speed and diameter of the impeller, you can directly calculate what is the power requirement which is asked in the question. So I am substituting the values here. NP as 4.454, P by rho, which is 968 kg per meter cube, Ni, which is 3 RPS, so 3 per cube, 3 cube, and then di, which is the impeller diameter, which is 0.4 meter, power 5. From this you get a power of 1192 watts, and hence the answer to this question is option B. So with this we wind up today's problem solving session. So as you can see here, majority of the question relates to the velocity components, the power number, mixing index, and relating a certain kind of impeller with the kind of application, whether it is for solid, whether it is for powder, cohesive solids, viscous fluids, and so on. So these are the major concepts that have been time and again discussed in the assignments and in the questions that we've dealt for the past 2 years. So I hope that this problem solving session will help you in solving your current assignment. So thank you.